Okay, so let's look at the two things we did here, which were when calculating Reynolds, we went from the density, free stream velocity, diameter divided by viscosity to the 4 times the mass flow rate divided by the dynamic viscosity, pi, and diameter. And the other thing we did was we went from our overall heat transfer coefficient straight into this is equal to 1 over I plus 1 over to the minus 1. All right, let's start with the top one. So what we do there is we don't have the velocity, correct? We have everything except the velocity. But we know that the free stream velocity can be related because if I do, let's change colors. If I do my mass flow rate and divide that by my density, look at the units. What I have here is kilograms per second. And down here I have kilograms per meters cubed. So I'm going to be left with meters cubed per second, a unit of mass of volume flow rate, volumetric flow rate. Okay. And I can find the same volumetric flow rate if I do my surface area, or my cross-sectional area, I should say, cross-sectional area, times my free stream velocity, right? Free stream velocity being perpendicular to the cross-sectional area. So that means that if I want to solve for my free stream velocity, all I need to do is multiply by a mass flow rate divided by my density divided by my cross-sectional area. What is a cross-sectional area? Well, if I have a pipe with a certain diameter, the cross-sectional area is going to be pi r squared or pi d squared divided by 4, right? Because obviously all I'm doing here is just substituting that I have my 2r equals my d. So I need to also need to square my 2 when I put it over here. So this means that my u is just mass flow rate times 4 density pi diameter squared. Okay, and then from here it's a simple exercise to let's do it here to find my Reynolds, because I know this is density, free stream velocity, diameter divided by the viscosity, and where I have my velocity I'm going to substitute by what I just found. So let's do like so. Which means that my density can be removed, and where I have 2 diameters I only have 1. So this leaves me with 4 times the mass flow rate divided by the dynamic viscosity pi diameter. Okay, and this is the one we used in the problem. Up next, the overall heat transfer coefficient. So what we have there is a tube. Let's draw a tube, or 30,000 of these tubes, right? And on the outside here, we have the shell with steam, right? And inside the tube, we have liquid water. So in order for heat, and we know heat is traveling from the steam into our water. So for heat to travel from the steam into the water, it needs to go through 3 different resistances, right? So the first one is when the steam finds the pipe. So there is a fluid interacting with a solid. That's going to give us a convective resistance. So let's put it here on the side, convective resistance. Then the tube itself, it's made of metallic material, but the metallic material does have mass, so therefore it has a conductive resistance. And then finally, the tube interacts with the water, so we're going to have solid interacting with the fluid, which gives us a convective resistance. So convective or conductive and R convective. Now, metal tube plus thin walled is screaming that the convective resistances, either one of them, is much greater than the conductive one. So much so that we can pretty much ignore this. So this goes to 0. Okay, and then this diagram with 3 resistances is further simplified into a diagram with only 2 resistances, right? Only the 2 convective ones. And the other thing to note is that these things are in parallel, right? Because there's no way for the heat to travel from the steam into the water without going through all these barriers, or through all these resistances, I should say. So that means that if I want to find an equivalent resistance, if I want to find, what's the equivalent of having only one single resistance here, all we need to do is sum up the 2 convective resistances, right? The convective of the inner plus the convective of the outer. All right, and then what is the overall heat transfer coefficient? The overall heat transfer coefficient is the equivalent of calculating the resistance, the convective resistance of the sum of r's, which would be just 1 over A overall heat transfer coefficient, right? So instead of having, this guy, we have one to rule them all. So what I can do here is, because I know the convective resistance of the internal one is just 1 over the internal area times H1, and I know the outer one is just the outer area, outer area times H naught. What I can do here is, because it's a thin walled, because the thin walled tube, this says that my internal area is very similar to my outer area. So I can just call them both area, okay? And then what this means is this becomes just 1 over area of 1 over the internal one, 1 over the external one, correct? If this is the case, now what I can do is I can substitute where I have my sum of r's, I can substitute sum of r's, right? So in other words, I can get this fella here, and I can substitute it in here. Okay, so this has to be equal to this. All right, let me just put this down so we don't have a mix of things going on here. All right. So if this is the case, you can see that we have 1 over the internal area on both sides of the equation, which means that, therefore, okay, 1 over u equals 1 over hi plus 1 over h naught. And now if I invert it, obviously, right, if I invert this guy here, I'm just going to have to invert the other one too. So it's going to be 1 over plus, and then invert it. And this is the relationship we had in the beginning to start with. Here you go. All right, and that's how we came to be. So, in an exam, you can jump straight into this if you have a thin wall situation. If not, you're going to have to do, you might not be able to do this, right? In this case, the question was asking us to, so we're going to have to find it somehow. And then you can or you can't ignore the conduction depending on your situation. So this step here depends on what the problem says, right? Generally, you can ignore it. All right, so if you have any questions, just drop them down below, and we'll talk soon.